we're given a triangle OAB, and angle OBA is 90 degrees. So I'm going to sketch a right angled triangle. Let's say the triangle looks like this. So here and here, we are having one of the corner as a right angle, and this will be OAB, and the corner OBA, this is 90 degrees. We're also given that OA, the position vector of this point A, this vector here is vector A, and OB, this vector here is vector B. And I'm going to make use of the fact that this is 90 degrees to try to show this equation here. So I'm going to go for OB, vector OB, and I'm going to go for vector AB. They are 90 degrees, so if I were to make use of a dot product, the result should be equal to 0. So OB is vector B. Dot AB is vector B minus away vector A. This is equal to 0. So if I were to re-express my dot product, it is going to be B dot B minus away B dot A. This is equal to 0. And what is B dot B? B dot B is modulus of B squared. And B dot A is the same as A dot B. So here we will have A dot B. This is equal to 0. And bringing this over to the other side, we will be able to make A dot B the subject. And this is equal to modulus of B squared. And this is what we are supposed to show. In part 2, a 1-mark question, we are supposed to quote the position vector of C. And according to the question, AB is equal to 3AC. What I personally like to do, instead of seeing it as AB is equal to 3AC, sometimes I would like to see this in the form of a ratio instead. So if I can re-express this, AB over AC is equal to 3 over 1. So AB is to AC is of the ratio 3 is to 1. And if I were to just plug C here, that means AB is going to be 3 proportion, AC is going to be 1 proportion, which makes BC 2 proportions. So with this setup, I can now make use of the ratio theorem to find OC. So OC, which is this vector C, so this vector C, if I were to make use of the ratio theorem, it is going to be 2 times of the opposite, which is A, 2A, then plus 1 time of the opposite, which is B, divided by 2 plus 1. So this is equal to 1 over 3 of 2A plus B. To find the length of projection, I'm going to make use of the magic triangle that I have highlighted on the Achevas TV. So for the magic triangle, I am going to redraw this diagram, but I'm going to focus on just OC and OA. Let me redraw it in a way that maybe it is a little bit more familiar to us in terms of our visualization of it. So if I were to make O here, C is here, and A is here. So this vector here is our vector OA. And we want to find the length of projection of OC, where this vector here is C, the length of projection of C onto A. So if I were to make use of the magic triangle, we are seeing a right angled triangle here, and we know that the length of the hypotenuse here, this length here is modulus of C, the length. That's why we are going for the modulus of C. And if I were to assign theta here, then this length, which is the length of projection using Tuacaso, this length is going to be modulus of C cosine theta. And because we see a cosine theta and we have used an angle that is between vectors A and C, so this makes it possible for us to make use of the dot product to try to involve the angle theta and these two vectors. So A dot C, this is equal to modulus of A, modulus of C, cosine theta. And instead of directly finding modulus of C cosine theta using this equation over here, which has a modulus of C cosine theta, if I were to make this the subject, modulus of C cosine theta, this is simply just going to be A dot C divided by modulus of A. So this is another representation for modulus of c cosine theta. I'm going to make use of it for part 3 to find the length of projection. So the length of projection is going to be equal to the modulus of a dot c divided by modulus of a. We are adding an extra modulus just to make sure that the length that we are finding is always going to be a positive number. So for a, I'm going to keep it. For c, I'm going to replace it by this. And for this modulus of a, since it is a positive scalar number, I'm going to bring it out of the modulus, which gives us a 1 over modulus of a. And within here, a, I'm keeping it. So it is going to be a dot c. C is what we have derived in part 2. So it is going to be 1 over 3 2a plus b. And 1 over 3 is also a positive scalar number. I'm going to bring it out of the modulus also. So we have a 1 over 3 modulus of a. So we have here a dot 2a plus b. Okay, and now we have 1 over 3 modulus of a. Re-expressing what we have here, it is going to be this dot this, which is 2a dot a, then plus a dot b. So this is equal to 1 over 3 of modulus of a. And what is a dot a? It is modulus of a square. So we have 2 modulus of a square plus a dot b. A dot b we have actually derived in part 1. We have shown in part 1 that a dot b is modulus of b square. So I'm going to replace this by modulus of b square. And one small touch up to this expression over here is an expression that is within this modulus that is a positive number. Okay, because 2 modulus of a square is positive, modulus of b square is also positive. So I'm going to touch up this expression here by re-expressing it as just the normal curve bracket, since the modulus doesn't make a difference. So my final answer is going to be this, with a modulus of a square and a modulus of b square within the curve bracket.